Hello, my name is Abigail Glover, and this is the video portion for my Fluent Project 1 for Fluid Mechanics with Dr. Ozbay for the spring 2023 semester. I already have my workbench pulled up for Fluent. As you can see, I have my 3 flows here that I did while I was working on the project. For the sake of this video, we're just going to go over here to Analysis Systems, click and drag Fluid Flow Fluent. First thing we're going to do is click Geometry and change this from 3D to 2D. After that, we're going to right-click and go down to New Design Modeler Geometry. You're more than welcome to choose one of the other 2 systems. I just found this was the one that made the most sense to me and was more user-friendly because it's a lot more like SolidWorks. I'm going to go ahead and apply my axes, double-click the Z to get it looking nice. We're going to start our sketch by going over to sketching and go up to rectangle. Now I'm going to put mine at the origin because this will make it much easier later down the line when we are inserting lines for our results. So after we do that, we're just going to go over here to dimensions. There we go. And we'll do a horizontal one as well. Now I'm going to go ahead and go up here and change my units to millimeters because that's what we're using for this project. And now I can edit my values. I did mess around a lot with the values, but for the sake of this, I'm just going to use what worked for me for each flow case. In this case, I used a bar that was 10 millimeters high and 500 millimeters long. But you'll see for the other 2 cases, I used different values for my system. But for right now, this is the 2. If you want to display the values here instead of your variables, you can go down here, unclick name, and it'll auto-select your value, and then you can actually see those 2 values. But I don't really want those in my way, so I'm just going to click out of there, select, and delete just so they're out of the way. When you zoom in, you'll see here is our system. So now we want to go up to concept, surface from sketches. We're going to change this to a box select, and we're going to create a surface from the sketch that we just made. Click apply and generate, and now we have a surface. That's all we have to do for this portion, and as soon as we go back to our workbench, we'll see that we now have a green check mark. So now we're going to move on to our mesh. There's nothing we have to worry about changing in here, so we're just going to double click and open up that process. Now, meshing is one of the longer processes. My computer is pretty slow, so I will jump ahead just to avoid you having to watch the meshing after I've completed it. But once we've got it open here, we've got our body. The first thing I like to do is to go up to Edge, and we're going to name everything. So you're going to select, right-click, create name section. And you're just going to do that the same for all of them. And then to check that we got everything named, we'll go over here to name selections. You'll see all of them. If you click them, you'll see where they're located. Everything looks good. So now we can get started on the mesh. I'm going to go up here and click. You can use these options up here, but I'm just going to right click, hit insert, and sizing. From here, I'm going to select the upper and the lower wall and click apply. We're not going to do it based on element size, but instead on number of divisions. So for this, I'm going to do 2500. And then we're going to change this capture curvature to no and change our behavior to hard. So we've got our geometry selection, 2 edges, number of divisions, 2500 hard, looks great. We're going to go up here and generate that mesh. So it's meshing down here. I will be right back once that process is finished. So now our mesh is ready to go. If we click up here, we'll be able to see all that. Now we're going to do the same thing for the inlet and the outlet. Click apply, change this to number of divisions. This I'll do 50. Change this to no. Oops. And we're going to change it from soft to hard. So we've got our geometry selection, 2 edges, number of divisions 50, and a hard behavior. You can go ahead and generate that. So now my second set of mesh is ready. I can see it when I click up here. It's looking pretty good, but now we want to do a face mesh. So we'll go up here, select face mesh, we'll select our geometry and apply. That looks fine, and now we'll generate. And if you select mesh up here, it looks completely black, but once you zoom in, you'll be able to see that super fine mesh that I've created. We want to make sure it looks the way we want to. Meshing is one of the more important steps of this process. If you get your mesh wrong, it can mess up your entire result section. This is looking great though. So from there, we're going to go back to our workbench. Going to right click and update, and as soon as we get that green check mark, we can set up for the result process. When you single click, you'll get this over here. I like to change it to double precision, but if you double click it to open the application as well, it will give you a pop-up where you can select it as well. I'm going to leave my solver processes at 1 and click start. So now that we're on this page, we are good to get started. The first thing I'm going to do is just go to my results section and my residuals. And actually, I'll change this after I change the flow. We're going to go from viscous SSTK omega to laminar. That's the type of flow we want. And now we'll go to residuals and we'll change all of these values. This is just a personal preference. But now that we've got that changed, we're going to go through all of our options here. So we've got viscous laminar. For our materials, we're going to do fluid and air. We're going to change our density to 1. And for this case, my viscosity is going to be 1e to the negative 5. I'm going to change and create and close. I'm just going to double click this and make sure that it does have air selected. It does. I'm going to close that out. And then I'm going to go down here to reference values and compute from the inlet and make sure that everything updates. Density is 1, viscosity is 1 to the negative 5. Perfect. And our reference zone is the surface body. These are both good. Don't need to change anything there. And under boundary conditions is where we're going to change our variables related to the system. So for the case of Poiseuille, we want an inlet velocity and 2 stationary plates. So for this case, my velocity, I'm going to change to 0.04 meters per second. And the reason I changed it to that is because when I calculate my Reynolds number with the other values from what I've set up, I get a value of 2000, which means that the flow is laminar and not turbulent. And that's what we want for this case. I did mess around with a bunch of other velocity values, but this is what I found worked for this case. This we're not going to change. For the outlet pressure, the only thing we're going to change is to make sure that we prevent that reverse flow. That way our flow doesn't come back into the system. And then we're just going to double check our lower and upper walls and make sure that they are stationary with no slip condition. I'm going to apply that, close, and check the upper wall. And they are both good to go. From here, I'm just going to double check my reference values. And then I'm going to scroll down and we are going to initialize. You'll see the initialization iterations pop up down here. Usually it gets to about 10, and then that's when we can get ready to run the calculation. So now we're just gonna double click run calculation. And we're gonna change our number of iterations. I think for the sake of this, I'll do 150. I usually do 200 to 500. And then we're gonna hit calculate. So now my calculation is complete. We can go back to our workbench and we can go to our results. Since I already have the green check mark on the design and the mesh, I'm just going to go ahead and exit out of these just so my computer doesn't lose it while we're trying to do the results. I'm just going to go ahead and put it in the ZAxis. The first thing I'm going to do is add my lines. I'm going to have a midline and an end line. So in this case, the length is 500 for the midline. We're going to be at 250. And we're going to do full length, so when we apply it, we can see it generate here. Then we're going to go ahead and add our end line. And in this case, we're going to go right before the end of the system. You don't want to be on the actual edge, because that can mess up your results. We can see it hanging out down here. And then I'm also going to add a line for the developing flow, and you'll see why more once we get into the chart. And that looks pretty good. We can always come back and change it if we decide that that's not what we need. But for now, we're going to go ahead and generate a contour. We're going to do symmetry 1 instead of pressure, velocity U. I'm going to change my number of contours to 110. And then we go ahead and apply. So here's our contour. It's a little funky just because the legend is in the way, so we'll go ahead and double click here. We'll change that to horizontal and from scientific to fixed. That'll clean it up nicely for us. So now going into our chart. There we go. We're going to go ahead and change the title. And then we're going to go into our data series. We're going to change this to our midline. And go ahead and label it. We're going to add our end line. And then I'm also going to add my developing region. For that, we're going to go here. We're going to change our X to velocity U, and our Y is going to be changed to Y. And then we'll apply that. The midline and the end line are overlapped right now. So if I delete this, you'll see that it was right over top of it. We'll go ahead and add it back. And now it's overlapped again. But the reason that that's happening is because our flow is fully developed by the time it hits the midline and the end line. So the reason I chose for my third line to be what I consider the developing flow is to show that it was at one point developing. And if we go here, we can actually update this value. You can see that it's curved differently. That's because the flow is still developing, whereas this is that fully developed flow. And then if we change that value to something a little bit greater, so it's a little bit further out, it starts to get closer to that developed region. So because my midline and my end line are stacked, I did add a third line just so that I could see that that flow was truly developing and not staying consistent throughout the system. With that, all we have to do now is export our data, and then we examine that after the fact. And that is it for the CoE Flow. Next, I will be doing the CoE Flow. So now that I'm back on my workbench, I'm going to start the CoE Flow in an effort to save some time. I'm not going to go through geometry or meshing again. I will say between my CoE Flow and my CoE Flow, the major thing that changed is I just changed the size of my system, the total length from 500 to 250, and the height from 10 millimeters to 5 millimeters to meet the conditions that were specified in the project handout. Other than that, the entire process is exactly the same from sketching to meshing, and I also kept my number of divisions for meshing the same. With that being said, I'm just going to go ahead and pop into what I already did and just go through the setup process and show the differences between setting up the CoE Flow versus the CoE Flow. So again, we're going to go to double precision, one solver process, and click start. We're going to go through exactly the same things we did the last time. We're going to make sure that we're in a viscous laminar flow and not anything else. And then we're going to go over here to our materials. Now in this case, I did make a change to air. The density is still 1, but instead of 10e to the negative 5 for our viscosity, I changed my viscosity to 1 times 10 to the negative 3. And again, the reason I changed this is just because the values when calculating my Reynolds flow and the velocity of the upper plate, I was able to get that Reynolds number of 2000, which again is a laminar flow. So we're going to keep this. This was what was changed between the last one, change and create. We're going to close that. We're going to double check our fluid again, and it is air. Now looking at our boundary conditions, the big thing for this one is we're not going to have an inlet velocity. So we have to change our inlet from a velocity inlet to a pressure inlet. So we right click, we go over here to type, and velocity inlet will be selected. We're going to select pressure inlet. So then it'll load up this screen. It'll come up just like this, but we're going to click that prevent reverse flow for the inlet. Apply and close. This isn't going to change. For our outlet, we're not changing the type of outlet it is, but we are going to make sure that our prevent reverse flow is also selected for that. And then we're going to look at our walls. Now the big thing is we're going to want our lower wall to remain stationary with a no slip condition, which we have here. However, for our upper wall, that's the one that we want to move. So when we open it, it's going to automatically select stationary with a no slip. We're going to change this to moving wall. And you can put your speed in over here. For this specific instance, I did choose 8 meters per second, and that seems really, really high. But the Reynolds number works out, and it gives me a high enough speed that on the contour chart, you can actually see the shearing that's occurring. I messed around with the values. You're more than welcome to mess around with the values as well, but this is what I found worked for me. I'm just going to double check my residuals are 1e to the negative 6. We're good to go there. And we're going to double check our reference values and make sure it's computing from the inlet. Our reference is still the surface body. Our viscosity is 1 times 10 to the negative 3, and our density is 1. So that is looking great. Now we're going to go to initialization, and we're going to go ahead and initialize the system. Once our hybrid initialization is done, we're going to double click run calculation. I'm just going to change the iterations for the sake of the video from 200 to 150. It does save a little bit of time. And then we're going to hit calculate. Now that we're back, our calculation is complete. So we're going to go back to our workbench. So I'm just going to hide all this stuff and go through it the same way I did with CoE Flow, just keeping in mind the changes that I made with the sizing. So the first thing we're going to do is go to location and line. We're going to do a midline. So we'll do midline 1. And because our length changed from 500 to 250, our value is now going to be 0.125. And because our height changed from 10 to 5, I'm going to change that. But we're still going to do 100 samples. You'll see that pop up. Perfect. Now we're going to add our end line. And again, we're going to do 100 samples. See it pop up down here at the end. So with that, I'm going to go ahead and create my contour. I'm going to do symmetry 1 and velocity U. I'm going to change this to 110 and apply. Now, just looking at this, this looks pretty good. Our maximum velocity is right around the velocity that we put into the system as far as that moving upper wall. And it looks pretty. We can see what's going on. That upper wall is moving, that bottom one is staying the same with that no slip condition. We're going to go over to our chart view, and I'm gonna insert a new chart so that I can go through the process again. We're going to add our 2 series. So in this case, our location is going to be midline 1 and endline 1. We're going to change our x-axis to velocity u again and our y-axis to y. And then everything else should be set for us. And we can see that once we apply it, it is. So you can see that it's a linear relationship up to about 8 meters per second, which makes sense because that's the velocity of our upper plate. It looks very pretty, and they are over one another, which we can see if we go here and we delete our end line. Now we just have our midline, so they are stacked right on top of each other. And then from here, we can export the data and evaluate it further. With that, the CoE Flow is complete. So now we will be moving on to the hybrid flow. So now the third and final case is going to be our hybrid flow. I kept it 250 millimeters by 5 millimeters for this specific one. So jumping into the setup for the experiment, we're just going to double check and make sure that it's double precision. We're going to do the same thing we did for the last one where we go through and talk about it. Now, the big thing with this flow is it is a combination between the Poiseuille and the CoE. So what we can expect is we're going to have an inlet velocity, and we're also going to have that upper plate moving. So we need to make sure that our model incorporates both of those factors in it. So we're going to start and make sure that, again, we're under viscous laminar and not anything else. After we have that set up, we can go ahead and check our results and make sure residuals are exactly what we want. In this case, I went with 1e to the negative 6, but it is up to you. Now going into materials, again, we're using, and the density is still 1, that hasn't changed, but in this case, I changed the viscosity from 10 to the negative 3 to 10 to the negative 4. So that is the big thing I changed here. So we want to make sure that that updates in our reference values when we get there. And again, the reason I change my viscosity or my velocity or any of those values is so that my Reynolds number stays around that 2000 to make sure that it remains a laminar flow. So we're gonna change and create, and then we'll close that out. We're going to double check and make sure that this is registering as air, and it is. And then we're going to go to our boundary conditions. So starting with our inlet, If it's carried over from the last one, or if you're starting from scratch, you just want to make sure that it is listed as a velocity inlet. If it's not, you can go down here to type and change it to velocity inlet. But we want to make sure we have that velocity inlet for this case. Now, in this case, I chose 0.8 meters per second to be my velocity, again, for that laminar flow with the Reynolds number. For our outlet, again, we want to make sure that we don't have any reverse flow. So we're going to select prevent reverse flow if it's not already selected. Then we're going to examine our walls. So our lower plate should remain stationary with a no slip condition. Stationary with no slip, and we have that. Now the upper wall is the one we want to make sure is moving. So it'll automatically be selected to be a stationary wall. We're going to select moving wall. And then for the speed of the moving wall, I chose 0.6 meters per second. From there, we're going to go to our reference values. We're going to compute from our inlet again. And we're going to make sure our density is 1 and our viscosity is what we put in. So I put 1 times 10 to the negative 4. This is 1 times 10 to the negative 4. So we are good in that regard. From here, we can go ahead and go to initialization. Once that initialization is complete, we're going to double click run calculation. This will automatically be set to 0. So we want to change our number of iterations. For the sake of this, I'll do 150 iterations instead of 200. And then we're going to select calculate. So now the calculation is complete. We are good to go back to our workbench and get set on the results. I'm going to double click results and we'll recreate them. So we're going to go up here to location and line. We'll do midline. We're going to do 100 samples and apply. And there is our midline. Now we're going to do our end line. Our end line has popped up here. And then the other line that I did was the developing flow region. In this case, I did it at 0.0075, and I will show that on the chart. But for now, for the sake of not just typing it all in again, this is one of the lines that I did examine for the chart. So from here, we're going to go ahead and create a contour. We're going to do our symmetry 1 and velocity U with 110 contours. Go ahead and apply that. And this is what it looks like. So these are the values that I'm getting from that contour line. Now we're going to go ahead and do a chart. We're going to include our midline. I'll use the ones that I just did. And then I'm also going to add that developing flow region. And you'll see why when it charts. We're going to make sure our x-axis is our velocity u and our y-axis is y. Click apply, and this is the chart that we get. The reason I once again did that developing flow region is because both my midline and end line are fully developed, and this is that combination between Poiseuille and Covet. You can kind of see that from this, but because of keeping it laminar and keeping that Reynolds number around 2000 and the specific velocities that I chose, our midline and end line are both fully developed. So in order to see that it wasn't fully developed from the start and there was that initial developing region, I did that developing flow region and examine that. And as you can see, it's not fully developed. It's not reaching that critical point. So it does progress over the course of the system. And this is really good too. I ended up messing around with this and the laminar flow assumption for both the hybrid and the Poiseuille flow. Once you calculate your critical length, you can actually plug that length in and you can see if it overlaps with your developed flow, because that's going to be the point at which the flow is fully developed. And then anything under that is going to be underdeveloped. But that is it as far as my results go. I exported them for each case, and then I examined them to get the maximum velocity and maximum height, which I will show here real quick. So for Poiseuille, we've got our maximum velocity ended up being 0.06 meters per second with a maximum height of 0.005. For the CoE Flow, same thing. I analyzed the extrapolated data. Here's our chart. Our maximum velocity ended up being 8 meters per second. Maximum height was at the height where that top plate is moving. And finally, for the hybrid flow, our maximum velocity ended up being 1.079 meters per second at a maximum height of 0.00298 meters. Thank you so much for watching. I hope you have a wonderful day and see you again next time.